Hi, I'm Chem's best friend. I make chemistry easy. I'm a graduate of MIT, and I have more than 17 years of experience teaching AP chemistry and chemistry classes. Please like and subscribe to my channel. And if you are interested in private tutoring lessons, the information is on the screen. Hi, ready to learn more about single replacement reactions? I am. Let's go. So here we have examples of single replacement reactions. And remember, in the previous video, I said there is two different types of single replacement reactions. Have a look. Do you remember how we introduced them? We had, in the first type, we had Adam and Barbara dancing, and then Charlie walked in. So when Charlie walked in, Adam and Charlie switched places. So now Charlie is dancing with Barbara, and Adam is by himself. Think of this as the boys switched places. Think of them as cation switching places, the metal displacing a metal. We will talk about this in a second. Or a second scenario could be Adam and Barbara dancing on a dance floor and Diane walks in. So the two girls switch places. So now Adam is dancing with Diane and Barbara is by herself. So in single replacement reactions, you can have metal displacing a metal or a halogen displacing a halogen. And we will talk about both types of reactions to show you what I mean. But I think the first thing would be to let's see actually a reaction in action. Let's see a video about one. So let's watch a video of a reaction between copper metal and a solution of silver nitrate. So I'm going to have a solution of silver nitrate. I'm going to stick a nice copper metal into it, and let's see what happens. So just a nice empty test tube, and here comes my copper metal, and there's a bubble in there. So I shook the test tube to get rid of that bubble. Okay, bubble went away, and have a look at this reaction. This reaction took place over 6 minutes, and it is fast forwarded. Whoa! Do you see that copper metal? I don't see copper metal anymore. I see nice silver metal spikes growing all over. So let's actually write about this. So here's quick pictures to remind you. And the first picture you see is I actually took a picture of this reaction from above. So the copper metal that you see is the piece of sticking above the solution that didn't react. And the one below, a little bit below, you can see that silver growing all over that metal. And this is the side. So what happened? Let's write this down. We had copper, solid. Copper was a solid. We put it in a solution of silver nitrate. And silver is +1 charge, nitrate was negative, and this was a clear solution, AQ. Now, let's see what happened. Well, we had silver metal forming, and then we had a solution of copper to nitrate. So in this reaction, copper, that's a metal, and silver right here, which is a metal ion, switched places. So let's write that down. So we then formed silver solid plus copper. Now this became copper 2 nitrate. And you say, how do I know it was a copper 2 charge? I'm going to tell you in a second, but first, nitrates are always soluble. So this is AQ. I have to quickly balance my reaction. I have 2 nitrates. I need 2 over here, 2 nitrates, and now we have 2 silvers. I need to balance, and I have to have 2 silvers. And right there, my reaction is balanced. So let's go back to the question, how do I know copper is a 2+ charge? And the reason I know it is there's a telltale sign. So chemistry many times gives you color clues. And that's what makes chemistry a little bit difficult, because not only you need to be good in math, but you also need to know things like colors. And have a look closer here. Do you see that I can see this turquoise, this light blue color forming? This light blue color forming tells me that I have copper 2 plus copper 2 ions swimming in a solution. That's my hint. Okay, so we wrote our reaction in a molecular way, even though there's no molecules, but people call it, this is a molecular form. We wrote it in molecular form. Let's write it in our complete ionic and net ionic form. But first, let's draw a picture. So, what is the driving force? We want to answer this question, but we're not ready to answer it yet. Let's draw a picture of what happens in this reaction. Well, what did we have? We had copper was a solid metal. It was put in a solution of silver nitrate. Nitrate was swimming by itself. Yes, and I have to quickly, I'm going to look back, I have to balance it. So I'm going to have 2 silver ions, 2 nitrate ions. And what happened? Well, I had silver metal formed, and I will need 2, plus I had copper nitrate. So I had a copper was now 2 plus ion, plus 2 nitrates. And this is AQ. Okay, let's actually draw it. So we had so we have our copper is right here, our copper solid, plus let's make silver ions. I don't really know which color. Let's make them nice pink. That's fine. So we have our silver ions swimming around. Let's make them. So this is my silver ions, and my nitrate ions, they can be light blue. That's fine. So this light blue sphere represents the whole polyatomic ion that represents the whole NO3 minus. And this will be my silver plus. And I need to have 2 of these nitrate ions swimming around. I'm going to put copper solid in my solution. So right here, let's just draw, if it's orange, this is going to be my copper solid. So the orange is representing as my copper solid. So no charge for the solid. Okay, then what happened after? What happened after? Well, I still have my 2 nitrates swimming around. That did not change. They are by themselves. And now I'm going to have 2 silvers. Now, this is not going to be ionic. They no longer have charge. So I'm just drawing that I have, they changed. So this will be my silver, and I'm going to have some copper ions swimming around, but they change too. So I'm going to make green by themselves. So green will be copper 2 plus ions, and red, pure red, is my silver atom, not ion. So this is what happened. And to emphasize that this is my new solid, I'm going to put it in a nice box to emphasize that. So nothing is swimming. So let's write our complete ionic reaction. Let's write our complete ionic reaction for this. Yeah, let's write our complete ionic reaction. Perfect. So our complete ionic reaction. Let's go. So what do we have? We have copper solid plus, let's write what we see. We had 2 silver ions swimming. We had 2 nitrate ions. Oh wait, we already did our complete ionic. That's right there on top. So that's our complete ionic here. We wrote that. Complete ionic reaction is right there on top. We already drew a picture. So now let's find our spectator ions. Let's quickly find our spectator ions. Which ones are they? What did not change before and after the arrow? Well, it seems like the only thing that not changed was nitrate. Nitrate ions were swimming by themselves before and after. Look at the picture. The blue spheres are the only ones that did not change. They are swimming by themselves before the reaction and after the reaction. So let's write our net ionic reaction of what happened. So net ionic reaction. So we had copper solid plus silver ions. And what happened? Well, now we're going to have two silver solid atoms plus copper is 2 plus ions. So, what happened here? What is different? What is the difference? So if we're going to say, what is the driving force of this single replacement reaction? Some of you might say, aha, I got this. I formed a solid right there. Here it is. I formed a solid. But who's to say that one solid is better than the other? Remember, one of your solids, copper, disappeared and a new solid appeared. You cannot say one solid is better than the other. So something else is going on here. Let's look closely. What's going on? Look at this. Copper is neutral. It's by itself. There's no charge. And when copper became ionic, what happened? Copper became 2 plus charge. So copper lost electrons. But when silver, we had two silver ions, each one with a +1 charge. They grabbed these electrons from copper and they became neutral. So now it became 0 charge for silver. So there was a transfer of electrons. There was a transfer of electrons here. Transfer of electrons. Whoa. So copper, what happened to copper? Copper lost electrons and silver ions gained electrons. So if something loses electrons, we say it was oxidized. Something gain electrons, we say it's reduced. And you say, no. Gain, reduced, yes. It has to go way back in history. And I will show you the example for this in a different video. Okay, when we will talk about synthesis reactions, it has to do with iron reacting with oxygen. And we say that iron became oxidized because it reacted with oxygen. But that's a topic for another video. But right now, we say the element that lost electrons oxidized, what gained electrons is reduced. And you say, how am I going to remember this? Oh my gosh, this is so hard. Well, you're going to meet your new best friend. And this new best friend is going to help you figure out all redox reactions. And guess what? You can use this friend on your tests and quizzes to help you. So you ready? So let's draw your new best friend quickly. Okay, let's make cute eyes, cute nose, smiley face, lots of hair. Whoa, lots of hair. Cute little ears. I think whiskers. Don't you think? Okay, quickly. Big paws. And the back paws. Oh my goodness. These are the big back paws and a tail. Meet your new best friend. His name is Leo the lion. So here's a name tag right there. Leo. Leo, what do lions say? Lions roar. He says, grrr. Leo the lion says, grrr. Okay, now how is Leo going to help you solve redox reactions? Okay, look closely. Don't blink or you might miss it. So L-E-O. Leo. Loss of electrons is oxidation. Leo. Loss, electrons, oxidation. Ger. Leo says ger. G-E-R. Gain of electrons is reduction. You got that? Okay. Good. Let's keep moving. So, what happens to this reaction? You say, now we're going to switch things around. Now, what if we have a solution of copper 2 chloride and we're going to put silver metal into it? You might say, oh, okay, that's easy. The cations or something that could become cations can switch places. And if you actually do this reaction, you will see that nothing happens. Nothing happens here at all. And you say, what? What do you mean nothing happens? Well, we got to look at something. To help you solve single replacement reactions and to figure out when will metals switch places, we got to look at activity series. And it's a great thing. So activity series is metals organized in their ease of oxidation. So the ones on top lose electrons very easy. They actually want to lose electrons. They want to be ionic. The ones on the bottom do not lose electrons easy. They prefer actually to hold on to the electrons and be neutral. So you're going to find the two metals that are going to switch places, that you think might switch places, and you're going to check. Okay, so also before we kind of go into this, I like to really fast get some layout of a land here. Look how activity series is related to periodic table. Look on top, we have lithium here, we have potassium here, and we have sodium. So what some of the very top metals, lithium, potassium, and sodium, which lose electrons very easily, let's find them on our periodic table. And you can see that here they are in our alkali metal family. Our first family here, we have lithium, sodium, and potassium. They lose electrons very easy. So next, on our activity series, we have what? We have barium, calcium, magnesium. Barium, calcium, magnesium, where are they on the periodic table? Oh, here is magnesium, calcium, barium. They are our second column, alkaline earth metal family. So this family, the first one, alkali metals, very reactive family. Alkaline earth metals are reactive, but not as much. Look where they are. They are on top of activity series, but not as high. Then we have our aluminum. Okay, aluminum is right here. We have our aluminum, but then we have this huge bunch of all these metals. We have magnesium, aluminum, manganese, zinc, chromium, iron, cobalt, nickel, tin, lead. Where are these guys? All of them are our transition metals. Transition metals are not that reactive. You can hold zinc in your hand. You can hold iron in your hand. You can hold nickel in your hand. The first family, alkali metals, you cannot hold in your hand. So here we have our transition metals, and we also had, remember, our tin and lead. Then we have hydrogen. Hydrogen kind of separates things. We have hydrogen, it's blue. And then we have copper, silver, mercury, platinum, and gold. Look at them. They are right here. I call this column the money column, right? Think about this. People first in antiquity had gold coins. They were the most expensive, the most valuable coins. Then, if gold ran out, they would make silver coins. Then we have also copper coins. Think of jewelry. So this, if you are interested in finance, this is your favorite column of a periodic table right there. Copper, silver, and gold. Now, look where they are. Copper, silver, and gold are on the bottom. Between silver and gold is mercury and platinum. Where are they on the periodic table? On both sides of gold. mercury and platinum. So you can see it. We have copper, silver, we have platinum, mercury, yes, and gold on the bottom. Why is gold so expensive? Look where it is on activity series. On the bottom. It doesn't react. It doesn't want to lose its electrons. It wants to be neutral. It wants to be gold. And then we have silver, the second most expensive metal. Then we have copper. They are great. They are also great because they don't react with acids. We will get to it in a second. So for this reaction, let's look. What about this reaction? Why does nothing happen when we stick silver into a solution of copper chloride? Well, let's find it on activity series. Silver is right here and copper is right here. So copper is above silver. Copper is above silver. Find the two metals you want to switch, and the one on top wants to be ionic, and the one on the bottom wants to be neutral. The one on the top wants to be ionic, the one on the bottom wants to be neutral, and we look here, and we have silver is neutral, and copper is ionic. So they are already what they want to be. They will not switch places. And in our first original equation, we had copper that was neutral and silver that was in ionic form as silver nitrate. And then they will want to switch places. Silver is on the bottom of activity series than copper. Silver wants to be neutral. And this is why this reaction happened. And you saw a beautiful video of actually what happened. So let's do one more example. And let's watch a video of a reaction between magnesium metal and hydrochloric acid. So we're going to stick, we had a solution of hydrochloric acid. It's actually very, very dilute solution. And I put magnesium metal into that solution. So what do you see? What do you see is happening? Look at all the bubbles. So this solution was very dilute, so you do not have very vigorous bubbles, but you have enough to clearly see various bubbles forming. Okay, let's write to actually what happened. And here is our picture to remind us what we saw. So let's write this down. So we had solution of hydrochloric acid. It was aqueous. It looked like water. We put magnesium ribbon. Magnesium was a solid ribbon into it. And what did we see? If we let this reaction keep going for a very, very long time, we would, of course, see lots of bubbles. But after it was complete, we would see that magnesium ribbon disappeared. And it would be pretty, the test tube would feel really hot. So we had bubbles. What was this bubbles? So what switch places with what? So something that's positive charge might want to switch places with something that might want to be positive charge. So hydrogen and magnesium might switch places. So let's write this. So we have hydrogen gas. So here is our bubbles. Now remember, hydrogen is diatomic, so it's H2 plus magnesium chloride. Now remember, magnesium is +2 charge. Chloride is -1, so I need to have 2 chlorides for this compound to be neutral, ionic compound. And based on my solubility rules, chlorides are AQ, except with heavy metals. Magnesium is not a heavy metal. And I did not see a precipitate forming, so I know that this will be AQ. And let's check. Will magnesium and hydrogen switch places? So let's write our complete ionic reaction. Let's write our complete ionic. What happened here? So let's go. So we have to balance. We have to put 2 right here. We have to balance our reaction. There we go. Okay, we had, so hydrogen, hydrochloric acid, AQ, ions swimming by themselves, right? +2 Cl- plus magnesium solid. goes to, what will they go to? Where we had our H2 gas forming, plus, now we have Mg2 plus AQ plus 2 fluorides. Okay, what is the same before and after the arrow? What is my spectator ion? The only thing that's the same is my chlorides. Chlorides are my spectator ions. So I'm not writing that down, just saying spectator ions. And let's write our net ionic equation. My net ionic here, so what happened was I have my 2 hydrogen ions reacting with magnesium solid, goes to H2 gas plus Mg2 plus. Now, notice this is not only balanced in terms of atoms, but it's also balanced, the equation is balanced in terms of charges. I have 2 times positive 1 charge. So overall, I have a plus 2 charge before the arrow. Now look on after the arrow, I have 1 magnesium, which has a plus 2 charge. I also have an overall 1 times positive 2 is positive 2. So charges are balanced. So what's the driving force of this reaction? Is transfer of electrons. So you know what's happening, you know what's coming up. What's oxidized, what's reduced? Leo, please come, help. LEO, loss of electrons, oxidations, gain of electrons, reduction. So let's quickly do this. What lost electrons? So hydrogen was positive. Now it had to gain electrons to be neutral. So hydrogen ions were reduced. And what happened to magnesium? Magnesium was neutral, and now it's positive charge, so it had to lose electrons. LEO, loss of electrons, is oxidation. Magnesium became oxidized. So that's my driving force. So I think we have a nice idea, but so far we saw 2 nice examples of the first type of single replacement reactions, where you had something that could, a metal that could be positive, switching with a positive metal ion, or hydrogen is also would be considered that. So we had a metal displacing a metal. But we didn't look yet at the second type, where we had a halogen replacing halogen. So we can look here. So what about these reactions? Have a look here. What about these reactions? So we have fluorine gas, so not fluoride. Fluoride will be negative charge. This is fluorine, it's neutral. Fluorine is going to be bubbled through a solution of sodium chloride. So I didn't put F2 gas because once the gas becomes dissolved in water, once the gas molecules swim between water molecules, they are AQ. This is why I put AQ here. Or what happens when you put a bromine gas, you bubble it through, you dissolve it in a solution, and you're going to bubble it through a solution of sodium chloride. What will happen? Well, you say, okay, let's look at our activity series to see what switches places with what. And that sounds great idea. Here we're going to look at activity series. And I look and I'm like, oh my goodness, I don't see fluorine or bromine or chlorine or iodine. I don't see any of them. What do I do now? Number 1, you don't panic. You don't panic and you don't cry, because you have a periodic table. Remember our periodic table? Here is our halogen column right here. Yes? So let's look a little closer. When we look at our periodic table, our halogen column, it's almost like the same thing as metals. The one on the top want to be ionic. Want to be ionic, the ones on top. But now here is the thing, it's non-metals. So it's actually a little bit opposite. So the ones on top want to gain electrons the most. The ones on top wants to be ionic. They want to gain electrons the most. The ones on the bottom want to be neutral. So your periodic table is your activity series for your nonmetals. So let's look here. So remember, fluorine is on top, chlorine is in the middle for us, and bromine is on the bottom. So let's look here. So we have fluorine is on top, wants to be ionic, chlorine wants to be neutral. Will the first reaction happen? Yes, the first reaction will happen. Will the second reaction happen? Will the second reaction happen? Well, we have bromine that's already neutral and chloride that's ionic, and chloride wants to be ionic. So the second reaction, there will be no reaction here. So really, really fast, this reaction, yes, it will happen. So let's actually quickly look into it. Let's write our complete ionic and net ionic, and we are almost done. So bear with me. So we have F2. Let's write this really, really fast. We had our fluorine was mixed with sodium chloride, and they will switch places. So it's our halogens that are switching places. Yes, our halogens. So what will happen? What will I get? Well, I'm going to get NaFAQ plus Cl2. Now this will be gas. You will see little bubbles. You might see little bubbles, but I'm still going to say AQ because it will be dissolved in water. You will not really see much. It will just be some color changes. That's all you will see. You will see color changes because each halogens have a very specific color. Like chloride gas, we can see here is this yellowish gas, poisonous. Bromine, you can see it's liquid. So here it is, it's the liquid, but then it also makes this orange colored gas. Iodide looks like little silvery specks. It's a solid, but it forms this very, very magenta colored gas, kind of like my shirt color. And something about chemistry that's an interesting fact is whenever you see colored gas, you run. It's poisonous. Any colored gas is poisonous. So this fact might save your life. Any colored gas, you run the other way. Now, non-colored gas, you don't know. It could be oxygen, which we need, or it could be carbon monoxide, which is really, really bad. So colored gas, run away. Non-colored gas, you don't know. But anyway, let's go back to our single replacement reaction. We were almost done. So let's write our complete ionic. You know what? We never balanced this reaction, right? We never balanced it. We got so much into talking about gases that I need 2 over here and I need 2 over here. And now I can write my complete ionic. So let's go. We have our F2AQ plus 2 sodiums. Yes, 2 sodiums swimming around, 2 chlorides swimming around. And we're going to have 2 Na plus AQ plus 2 F minus AQ plus our now chlorine, a dissolved gas. So what's the same before and after the arrow? What is the same? Well, the only thing that's the same is our sodium ions. So sodium ions are our spectator ions. And now let's write our really, really fast. Let's have our net ionic. Net ionic. So what do we see? What happened? So we have F2AQ reacted with 2. So fluorine reacted with chloride, yes, to form fluoride and chlorine. All right, and you know what question is coming up. The last question, what's oxidized, what's reduced? What was oxidized, what was reduced? So we had F2, which is neutral, right? Fluorine was neutral, and now it gained electrons to become fluoride. So, gain of electrons is reduction. Remember? So this is our fluorine was reduced. And chloride was negative charge, and now it's neutral. Yes, so it lost its electrons. Leo, loss of electrons, oxidation. So chloride was oxidized. And that is it. We did a lot. I hope you can keep it all in your head. And thanks for watching, and see you next time.